Okay, we will start or continue our discussion on curve of statical stability. Okay. See, in the last class we talked how to establish statical stability from cross curves. Today, what I will initially discuss is the various characteristic of this curve, because this particular curve actually characterizes the vessel's stability over the entire range, vessel static stability. See, you have something like this, theta versus, this is of course I always write this for this curve is always unique for a given displacement given kg. We have to always remember that. Now you see, last class we mentioned that this is actually normally called the angle of vanishing stability, say theta vanishing, let me call this is small. This is actually range of stability. Etc. Now let us see, let us discuss a little bit about the property of this curve. Number one is that most ship actually what happen as it keeps tilting, it increases, because you can see it very intuitively that, see, if you think in terms of I, if you think that this is my initial see my configuration initial is like this, so my stability depends on this parameter. Let us say that I think that my initial condition is like this, then it will depend on this I. So essentially this is of course very rough explanation, because as the ship tilts, the water plane area increases, you would expect it will have a larger restoring moment, because restoring moment is in proportion to I of that water plane area. Okay, see here it will be I of this area about this line, some line through this, etc. So that is why Z curve normally increases, but then what happens, there is a point where the deck edge gets immersed. From that time, normally that happens when this reaches maximum. Normally, this is why it goes to half. After that, you see it begins to come down. That's when it begins to come down. This is exactly what most ships behave. It has an increase here, mostly around this. It is not exactly that this maximum is corresponding to this. That is not easy to, but roughly it will be always around that, within 5 degrees definitely. That is one point. Second point is that supposing you are reducing this GZ, in other words, I am raising kg. Suppose there is a ship here, my G was here, and I am raising it to G dash. What would happen? GZ will of course come down by GG1 sin theta. Okay, but that means that from here I have to take this GG1 sin theta. Now remember, why, if you look at that, you will find these arrows are increasing as I go up, because GG1 is a constant, but sin theta normally goes up to 90 degree, not 9 more. So therefore what happened, this will become like this, and the range will of course come down, and this gap actually goes up, this is probably more so. This is another thing, this increases.
That is the G shift.
This is actually G1 sin theta. See, this was my original GZ, this will be my G dash Z, the real GZ, when I have raised the CG to some extent. Okay, so it comes down. Now this is also explained from the slope. If you look at the slope here, this slope here is my that dGZ by d theta is Gm. Okay, this is obtained from the curve Gm cos theta. Now if you look at the other curve here, we will get the slope as dg by d theta. This will be my, say, G dash m dash. Let me call this new G. Now we can also find out that this formula actually matches very well with the previous one. See, now Gz is this Gz minus Gg1 sin theta. So d by d theta of g dash z becomes d by d theta of g8 minus gg dash d by d theta of sine theta. Okay. At theta tend to 0, we are all doing at theta tend to 0. So this is my gm, this is my gm original, minus this becomes gg dash, because you see d by d theta sin theta is cos theta 0 becomes 0. Now you see that therefore gm has reduced by gg dash. That is exactly what has happened earlier also, no? Supposing my m was here, g was here, and if I raise g to this thing, then my gm reduced by this much amount. So this is also proved actually from the theory. And if I bring it back, this one again, see the slope, the original slope was this black line. Say if I take it 1 radian here, now the reduced one becomes this one. So this becomes my nu gz, this distance, that is g, no sorry, new gm, this is my old gm, and so therefore this is my gg dash. Again it makes sense, because here this actually, if you look at that, it basically makes sense that you have just pulled it down. Now what therefore you have done is that if I had this curve, again theta versus gz, by reducing that, see, as if I am, you imagine that somebody has some rope here, and if I increase it, I am basically pulling down the curve, I am just pulling it down, I am making it by raising it more and more down. Here comes the question of this S curve. Now supposing I made it down so much that it become negative here, because you see gm, g dash m dash equal to gm minus gg dash, that we said. Now so my initially g was here, my m is here, let me say I raise the g beyond that, I may raise the g above that, then what would happen, this curve will become negative, slope become negative, this become here, but you want it to actually go up like this, because you do not want the ship to sink, and this is possible only if the curve has, see, this part is a constant which is gg dash sin theta, this difference. Okay, sin theta curve, if you look at that, sin theta actually is a curve which goes like that, there is no inflection. Therefore, but this curve tells me that this particular curve tells me that it must actually increase and go up like this. So this curve must be minimum a cubic curve, otherwise if there is a second order curve, it can only go like this. Is a linear curve, it goes like this, only cubic curve can go like this, at least cubic. You see, the by theory, if it is a straight line, I will just this make it more clear. See, this is a straight line, this is a parabola, y equal to ax plus bx square, this is y equal to ax. Okay. If you want a curve like this or a curve like this or like this, then you must write y as ax plus bx square plus cx cube, plus higher may be there, but at least up to this. If you do not have this, you do not have actually this S curve, okay, the point of inflection. Now we have found out here that I am, if by reducing it from this curve a constant term, what I am reducing is a sin theta. This final, see, let me say that again, g dash is gz minus gg dash sin theta. Now this is not having a point of inflection, it is not a cubic curve as such, in a at least small angle. One can say it can be, but it is within this 90 degree, it is going like that. Therefore this must be a cubic curve. See, if this has to be a cubic curve, then this must be a cubic curve, at least cubic curve. That means it must go like that. Therefore if there is a ship, you consider a ship which has a gz curve like that. This is not a good shape at all, because this shape, by some chance, if you have made it gm negative, it will simply sink initially. That means if you by some chance raise the weight to a point where initially it is unstable, till slightly it will just turn. This is what happens to submarine, which we will discuss that. So one of the characteristic that you want for a ship is that it should have, the ZZ curve should have a point of inflection, a desirable property. Let me write this way. Or we can say should be at least a cubic curve. This is the mathematics part of it, but most of us don't realize. Now what we will discuss, that what happens to a typical ship. Is it usually a cubic or it is not? We will discuss that now in a minute. But this is a property that becomes important. It is fortunate that most typical ship forms actually has a cubic nature, you see. Why now, why it is cubic nature, I will explain that from physics, from rather physical explanation, you see. Now you take a ship like that, just wall sided shape. Now we have seen that wall sided shape, what happens, that as the angle goes large, basically B goes here as well as B goes up here. See, essentially something like that, center of buoyancy not only moves on the side B, it also moves up. This upward movement gives an additional ZZ, delta ZZ type. See, this center of buoyancy, okay, we'll write other way around. Just one case, if the center of buoyancy has just moved here, then my force is like this, G is like this, my GZ is this. But if it moves also, I am just drawing an exaggerated diagram, it will never move so much. If it moves up, then my force is like this, my ZZ is increased by this much. So my GZ gets increased. Therefore, what happened, that as the angle goes up, my GZ goes up. Initially it goes small, later on it goes up. Now you see what is the parameter on which it goes up. You will find out that the parameter, this thing, without proof I will tell you, this is normally a function of the water plane area, that instantaneous water plane area. Normally, that means normally a function of this B. See, this I am telling here without proof, because what happened, if you think this, if you consider here this B to be increased, what happened, I'll give an explanation of that, why it is so in two cases. See, we want to have it going up, okay, small and going up, and you want to make this more. If this is more, obviously then GZ goes up higher. It can be less, can be more. Why it is more for a ship? See, we will take an extreme example. You take a ship of this type. Okay. Now what happened? When it goes up like this. Now you see, center of buoyancy, this much is removed here. So what are buoyancy, first of all, goes more, shifts more this side. This part is larger than had it been through this. You see, because what happened, you are shifting it, this weight here, to a larger extent, as if you are taking this weight and putting to a further on this side. If you consider this with the other case, say suppose this is a hypothetical case, in this time what happened, the water line will go actually like this. So the shift of B is lesser. This shift of B in this case is less than in this case. I don't know if I am clear. Again, I want to explain that three cases, then I should do that along with that with this three case. Take this case, this, there is a certain amount of shift of B. In this case, it is going through this only. See, therefore, there is a certain amount of shift of B. Now, supposing the line was actually through this, what would it would have meant? It would have meant that more liquid from here has been shifted to that side. Shift is more towards that side because it is at least this one. So the shift of B would have been more. If it was smaller, if it was here, the shift of B would have been less. So normally, if it flares up, if the ship flares up like this, the shift of B will increase. If the shift of B increases, obviously, first of all, GZ will increase. Okay. The second thing is that this part, you see, because this is higher here than this. Now, if you consider this way, in here, because this part is above, the rise of G also is more, because there is more weight added on the top. See, this weights are sharp up. This point is higher, this particular point, this much compared to this. So if you say that here what happened, the weight is shifted, the center of gravity is shifted 2/3 of this height. Here it is 2/3 of this height. This height is typically little more than that, because here the the shape was like that, so the shape is higher. See, if the hull was like this, then this would have actually gone to higher point. So therefore, the center of gravity of that vertically would have been higher. Effectively, that means that you have shifted the weight further this side, further up, and that you do what is that increase the rate of GZ increase will become larger. So that means initially GZ is increasing at certain rate, but as angle goes up, it goes up at higher rate. Okay, then what happens? This deck edge immersion begins to come. After that, this increase becomes falls down. Then it begins to drops down. Therefore, initially it goes up. Then because it has to come down after that, there is a tendency of coming down. Now, see, coming down is explained because water plane area is reducing, but coming up is explained from this part because of this effectively increase of I, at this region. So therefore, now I know that it will come down somewhere, and here it will start from here. So it could have been like that, but I know that here it must come up at a larger rate, and that explains why most ships actually have a flare, a such kind of thing. Wall-sided vessel we know it has, because wall-sided vessel formula itself tells me, because it tells me gm sin theta plus some half bm sin theta tan square theta. This part actually is a theta cube curve. In fact, if you take expansion of sin theta, you say sin theta is theta minus theta cube. There is formal formula there like this. You will easily see that. I am not going into the mathematics of it, but you can easily see that by an expansion even up to a small angle. But the point here is that this is interesting, because this happens to all ships, and this is one of the reasons from stability why most ships have this kind of flare preferred. Of course, not only one, because people want to have larger deck area, but flare always gives a higher stability. Why I mentioned that today in some of these ships, the Gardner and all are building called stealth ships, where it turns out that if you actually have this underwater like this, above water, it is better from stealth point of view. What happens, this is a new concept US Navy is exploring, and even in India, Gardner, the new ships are having this stealth concept. When this acoustic radiation are sent, you see what happens, all these are detected by only acoustic signals. Now if you put it up, it turns out that most signals actually go up on the sky. It becomes difficult to, if you upward slope is there, it does not go back to the signal. So upward is better, this like a tumble home, but it was never done before, because it always gives a less stability. If you do that, your GZ curve will come down like much. It will actually, yeah, it come down. But obviously, this is why typically most ships did not have that. But Navy now is exploring this, because they are actually putting G sufficiently down. See, stability for them, if you look at the naval ships, they are stable up to larger range. They actually have much lower G. Excuse me. So therefore, earlier because of stability that was not there, but nowadays they are exploring it. But this is the reason why a flare ship always will have a GZ going up. This is the explanation I am giving purely from a physical consideration. If you work the maths out, you can see that in case it is like this, you will always have this GZ expansion a theta cube type function. You can always show that, but no point of going to the maths right now. Okay, so this is just an explanation for the GZ curve. So let us see something else about this GZ curves. About see here. Okay, let me see a ship. Now you have a GZ curve like that. Suppose you are increasing the freeboard. Okay, freeboard is here. Let us see. Then what happens? See, earlier the deck edge immersion was at this angle, but now the deck edge immersion will be at larger angle. Okay, so what would happen is that the deck edge immersion will get larger angle. You would actually the GZ will be actually initially it becomes here, but it it will increase like this normally. So a raise of this thing will obviously increase the range of stability. That is also obvious because you have got more reserve buoyancy now, more part of it here. Now if you increase the breadth of the vessel, then what happen? Obviously I goes up, so initial slope will become more because GM must go up. Okay, so GM will go up, but on the other hand, the deck edge immersion here, earlier it was at this angle, but now the deck edge immersion is smaller angle. So it goes up, but actually it may this coming down becomes at a smaller. I mean this top is reached earlier, and it may come down like that. That means the initial slope is more, but the maximum value, maximum zigzag angle occurs at an earlier angle because the deck edge immersion occurs at an earlier angle. So these are some typicalities, and same thing would happen if you add superstructure. See, if you have a superstructure added, some superstructure added, the effect is same, like increasing freeboard. The effect is the first time. Stability will normally increase. If you, yeah. Roro ship and all. If you have now here, when I say superstructure, watertight superstructure, I mean where you can completely make the openings weathertight, etc. Now the second thing is that, or rather other thing is that, supposing the ship, see we have talked about rise of G, what happens if you raise the G, of course it comes down. What happens if you shift G? Suppose there is some weight, you shift it on this side, then what happen? G will shift to this side, you are already will have a angle of hill which will be given by that, GM into theta into displacement will be equal to WD. This angle will be there already, okay. But the question is that here, because there will be already an angle here, it will be somewhere here, and the GZ curve will actually become like this. Now we can see from other way around this particular graph, what would happen is that initially here, from the diagram, my G was here and B was here, this was my GZ. Now my G is shifted to this much, so my GZ has been reduced by this much amount. How much? It is GG1 cos theta amount, because this is theta and this part, this if you this much, this is G, this is G1, this is cos theta, this is G1 cos theta. Initial, this is Z point, so it is reduced by that much. So therefore it is basically reduced by that much, okay. Now if you see now here that this reduction, that is interesting, when theta equal to 0, this reduction is exactly GG1, this is GG1. But this reduction actually now, as theta goes to 90 degree, this reduction reduces. So therefore this becomes, it catches up with this more or less like this. So the effect is felt at smaller angle more, larger angle the effect is less, because that cos theta is such that the cos theta tends to 0 as theta goes, more and more it increases to this thing. So these are all some kind of a characteristic of the this static stability curve. I was telling about this submarine. Before I go to this dynamic stability, let me talk. See, if you take a submerged body, and for submerged body there is a G here, there is B here, and if it tilts here, supposing it has tilted like that, then G is still here, B will be somewhere here. So B here, G here, and GZ is GB into sin theta. That's all, because always the B will be through this point, G will be through this point, and GZ will be this, okay, for a submerged body. This maybe diagram is not, let me draw another diagram like this here. Say this is the submarine which is tilted here, so the G was here, force acting here, B was here, force acting here, and this is my GZ. So GZ is GB sin theta. Actually what happens is that B becomes M, so GM is GB for a submerged body, okay. And we know that GZ equal to GM sin theta, this holds throughout because there is no m here. See, earlier case why it did not hold good, because m was defined for a theta small. So this, see, this expression did not hold good for a shape only because m was not a constant, m was a function of theta. Had m been a constant, it would have held good, but now my m is constant at b, therefore it becomes GB sin theta. See, b does not depend on theta here because it's submerged body. It will be see, it is a centroid of the location, it will remain on that line where it is. So now if you see this expression sin theta gz, how the curve look like? It will be a sin theta curve. That means if it is 90 degree here, it is 0 here, the gz curve is simply like this. Yes, this is GB sin theta. So d by d d theta of gz equal to GB equal to GM at theta equal to 0. These all known. Now you are reducing this. As you reduce that, what happened? This new one becomes GB sin theta minus GG1 sin theta. This is actually new, say G that GB minus GG1 sin theta. So okay, so this becomes my new GM, or you can say initial stability. Now what happened if you now make it negative? That means if you reduce it comes like that, it comes like that. You go more, it will simply come like that. There is no way this curve can actually, if it is negative here, you see, it will remain negative fully. See, if this is negative, suppose this is negative, then up to theta equal to 90 degree it will become negative. It will simply become like a negative curve. Okay. So therefore what happens for this particular fully submerged condition, either the shape is stable or unstable. There is nothing like range of stability that it will be stable for 0 to 10 degree and then unstable. Either it is this way, or rather let me say it is this way, or it is this way. As simple as that. If you do that, it will simply turn turtle, it will just go upside down. There is no sort of in between position that you can have on this. So this cannot have an angle of log. This is the question that I wanted maybe I have asked. For a submerged body, you cannot have an angle of log. You see, there is no possibility of angle of log. For the angle of log concept is valid only because of a surface vessel, and you can also see that is because of the term BM. See, there is a GM and BM there, and BM will exist, non-zero value of BM exists only for a surface vessel. You see, a wall-sided formula tells me, no, GM sin theta plus half BM sin theta and square theta. Now for a submarine body, B is equal to M, so BM is always 0. So you don't have that for a submarine. As a result, you cannot have an angle of log. This is very important for an angle of log, which will exist only for a surface ship. So surface ship, therefore, people are in some sense luckier that it may be bad but may not sink. You see, you may still survive. Excuse me. Let us now talk about a different concept called dynamic stability. This of course is again a little bit of misnomer, but we call it so. Now here, instead of Gz, I am going to multiply that with weight. See, this is for a given displacement in kg. All right, okay. Now Gz was a righting moment, righting lever. Sorry. So Gz is but what is righting moment? Righting moment is the weight of the vessel into Gz. That is that's why I write weight. Some people write displacement, but I like to write weight, and I will always use in my class this as G into this mass displacement, which is same as rho G into V. I am always consistently writing this as volume meter cube, this as tons, this is kilonewton. Okay, I mean we are not making a mistake on that, we are going to keep that because this is a consistent SI unit instead of confusing with ton force and all that. Now the writing moment is W into Gz. This is in kilonewton meter unit. Okay. You see the nature of the curve remains same. In fact, you can I mean if one is sharp enough, one can put simply two scales, one for Gz, one for another scale with that scale factor. See, supposing it is 10,000 ton, then you put, say, let us say this is 0.1, 0.2, 0.3, 0.4, then you say this is Gz and this multiplied by 10,000 becomes equal to writing lever. So it is just a question of scaling. You can write another scale this side or another scale this side. So one curve actually tells me both, because it is a multiplication with a constant number. Now what happened? Concept of dynamic stability. Supposing the ship was in some angle here, let us say theta. Say supposing the ship has been held to an angle theta by some external force. Now you want to further heal it to an angle theta plus d theta. Say this is by a small angle. So the ship is already healing at 30 degree, you want to just heal it to 31 degree. Now as you keep healing the ship, the restoring moment tries to bring it back to it. So the energy or the work that is done, see, work done is always force into distance, right, or moment into displacement in the case of distance, or moment into angular displacement, which is the same thing. That is that by definition. See, if I take a weight and you try to shift it so much, the work that I have to do is that the force that I am applying and the distance I am moving. Now whenever I am trying to move the ship from this angle to this angle, I have to work against the restoring moment, because the restoring moment is at every point trying to bring it back. So the work done becomes the work done to heal the ship from angle theta to theta plus delta theta is same as the work done by the restoring moment, because the work done must get balanced, and this will be given by obviously theta 2 into, by definition, the Wgz into d theta. That means this area. So this is only from this small part. Now supposing I think what would be my work done to heal the ship from 0 degree to some angle, 0 to theta degree. Obviously the work done to heal 0 to theta will become 0 to theta W Gz d theta, or we will go to the next one. So it will turn out therefore that if you want to do work up to any angle, then the work done, see, if you want to heal the ship from 0 to this angle, this any angle here, the work that you have to do, see, I don't know how to put it this way, but without reason a ship cannot heal. Something would have applied some moment. So there is an external agency, somebody had to push it. You know, if it is you're doing a model, you are by hand pushing it or whatever. So there is some work that has to be done. There is a force that has to be applied against a resistance. What is the resistance? As I push it, the ship is trying to actually come back to its original position. This is the resistive moment. So if I want to heal the ship from 0 to theta degree, then what happened? The amount of work I have to do becomes equal to this area. And this, so I will write it down here, work done to say we call it h theta. So now what happens, therefore, supposing I plot a curve which gives me this the you know the ordinate here is my h theta, or h theta is equal to 0 to theta w g. Okay. But we are defining that, then this h theta is called dynamic or dynamical stability. People, both words can be used. Some people use dynamical stability. Now here I want to again stress certain things. See, from again basic mechanics, this is another of this typicality of our naval architecture profession, use of the word dynamic stability. See, in basic mechanics, a system is called statics if there is nothing changing with time. Everything is there is no velocity, there is no time dependence, and you call a system as dynamic if there is something changing with time. Say position is changing, so there is a velocity, v is dx by dt, then it is a dynamic system. Force is changing. Whenever there is a dynamic system, there has to be some motion or some change with respect to time. Therefore, whatever we are studying so far actually is hydrostatics. Really speaking, there is nothing changing with time. I am shifting my healing my shape. You may say position changes, but the corresponding force because of the change is not considered. We assume that as if it has been changed and you have fixed it. What will be the force coming? Hydrostatic force, as if you have changed further and kept it fixed. Okay. Basically, we are always studying hydrostatics. That means due to change there is no force. See, there is no force coming because of the fact that I am changing theta with respect to time. So there is a theta dot. But in my calculation of so far hydrostatics, there is no force which is function of theta dot. It is a function of theta, but not function of theta dot. Therefore, strictly speaking, it is not at all a dynamic system. It is purely hydrostatics. But unfortunately or fortunately, in naval architecture, we call this dynamic stability. Okay. That is because maybe a new term, but it is strictly not really a dynamic stability, it is a pseudo dynamic stability, one might say. The word dynamics, some other profession people may object, because there are other cases of dynamic stability with respect to direction. When a ship moves, when you are trying to move, should it maintain a steady line, there is a stability concept there. That is dynamic stability, because the ship is trying to move along a line. This is really not, I mean, we call it dynamic stability, but let us be in our mind clear that this dynamic is not connected to anything related to rate of change with time or change with time. It is purely a pseudo dynamic concept. Okay. Excuse me. Now, the reason we call this dynamic stability, there is a reason behind that. Everybody wants to find out, you see, what would be the amount, the healing angle if there is a certain external healing moment applied. Now, for most ships, what would happen, that you have, for this particular ship, mostly wind blows beam direction, and it is a wind that causes the ship to heal. It is an external, say, wind. Now, you can also have different kind of environmental excitation. For example, there can be a wave here. Normally, the wave case we are not considering here, because this becomes a part of sea keeping. It's a dynamic rolling. It does not give a steady hill. There's a wave comes, it will tilt to this, again come back again. It will what we call rolling. In other words, rolling is nothing but dynamic hill. That is hill with time. But so here normally we consider the wind healing moment. Now, what happens? Suppose suddenly there is a wind that is sort of applied. So, what would happen? See here, this is my restoring moment, say W into G, restoring moment here theta. Now let us say there is a wind heeling moment. See, there is a wind force here and the ship will turn about some point, so there will be a wind heeling moment. Say m wind, let me call. So this m wind will be applied on the ship, it may be something like that, say m wind. Now you see, the ship will obviously, again by theory, be at equilibrium when my total m is 0. That means my m wind equal to wzz. You see, the total moment on the system must remain 0. This is the basic condition of equilibrium. As long as the Newton has said 400 years back that as long as a force or moment exists, the vessel will keep on accelerating, or because mass into acceleration give you force or moment. So as long as there is a force or motion existing, it will keep on changing. The change will stop when the total force and moment on the system becomes 0. Here there is two force, as it tries to turn up, this wind gives a moment this side and it is countered by this restoring moment, and it will obviously stabilize at that angle when the two are same, which is known in this diagram. This will be at this point, fine. But the main issue is not that for dynamic stability, the concept of dynamic stability. It is connected to area. What happens is that when the wind blows, it has some energy. Now this energy, now according to again basic principle of conservation of energy, this energy must get absorbed by the work done by the restoring force. That means if you give a push here, it will keep on tilting to some angle initially where the total work done by the heeling moment becomes equal to the work done by the restoring moment. It will go up to that point, but at that particular point the two moments are not same, so it cannot stay there. See, it will come up to that point, but the moments are non-zero, so then it will again come back on this side. Then again it will go down, so it will oscillate a little bit till the energy gets dissipated. What would happen? That there will be viscous phenomena like wave formation, whatever, that will eventually dissipate. But in the first shot, it will go to some angle here where the work done by the heeling moment must equal the work done by the restoring moment. Okay, so let me say this, say theta max, let me call this is theta steady. So I will just write down theta steady where m is 0, that is mw is wzz, that we know, but that is not I mean the critical thing for us right now. Say theta maximum, it is where the work done by mw equals by delta or w. Okay, so let me go to the next one, how this comes. Maybe we should draw now in a different color this diagram. This is again I am drawing the same thing. Now let us say by dotted line, this is the area under the curve, and area under this curve is going to be of course initially 0, but it increases and also maybe decreases, something like that. This, let us put another curve. See, let us say this curve heeling moment is written as this is okay, and this one, this curve is moment. So this is equal to 0 to theta w. Now the thing is that it will basically go up to a point where that two work dones are same. That means up to this point, at this point, if you do here, this is the point here where the work done by this and work done by this are becoming same. So what will happen? The ship will therefore initially heal up to this angle, then it will oscillate back here, and ultimately it will stabilize at this angle, theta steady. So now what happened? Now we will see why the area becomes important. See, it will actually heal up to this much. What happens, supposing this angle is basically beyond a certain extent, which we will discuss immediately, I mean very shortly, then sometime it may happen that the ship simply capsizes. So we have to ensure that theta m is such that the ship do not capsize. This is why this concept becomes important. You see, theta m should be such that see, this is actually something like this. You know, suppose there is some system is there, some spring system is there. You see, if you oscillate that, if you give a force, it goes and comes back and oscillates. But there may be a point, if you give initial force and it goes more than that, it will just go down. Okay, this is what exactly the same thing. Every system has. See, if you see even if a HER also, if I rock like that, you know, there is an up to a certain angle I can rock. But if you go beyond that first shot, you just fall. Exactly the same idea is here. Okay, so now let us see what is the condition for us to ensure that theta m is not exceeding that that critical angle for capsize. Now, I mean, I drew these two area diagrams, but that is not probably necessary here. If I draw this again, and now if I draw again. So look at that. If this is my theta maximum, what we are saying that area under this, see, if I call this O, A, B, C and D. Now theta maximum obviously is that angle where the area A, B, C, O is equal to the area O, D, C, O, D, C back to O, let us say. Okay, this area must be equal to this area. That is the condition. See, in other words, it will come up to that angle theta m where the two areas are same. And obviously that we can see that this is essentially means it will come up to that angle where this area is equal to this area. Okay, essentially it is where this area is same as this area, because this is common to all. I mean, to say that this area is equal to this area is equal to same as saying that this area must be equal to this area. Okay, now think of it. Supposing the wind healing moment was too large. Let us say the case 1 when the wind healing moment was too large. So the wind healing moment is something like that. Then what happened? There is not enough area here. There is no angle. See, it would have. It cannot heal up to this much because this area available is less. We'll draw another diagram for that. Otherwise, it is getting this. Supposing it is here. Now, ship has healed beyond that. Say this angle, but this area is not enough. So it will go more than that here. It will keep on going more than that. It turns out that even up to this much, the area is not enough. Then what happens? It will heal further. But if it heals further, then there is no way that the area can become same, because at this point, if you see this two area curve, this area curve was actually going up here. I mean, the area the dynamic stability curve, it basically was going up here, then reducing from this point because the rate reduces. This one on the other hand is going up at a higher rate. See, the area under that was something like that, but it is the area under that, if I see this area under this, the full thing, this basically it is always becoming more here, because you see at any point here the area is more here. See, this is what is happening, that if this was too large, it never cuts. If it was not large enough, it would have cut at some point.
So this curve you're drawing for the area.
Area. Now I'll explain that in the next one slightly better, because this maybe is little confusing here. See, we will draw two curves separately. That will be easier. This concept is very important. That is why we are sort of paying attention to that. See, this curve here, I am drawing the area separately. Okay, I am drawing the area separately. This is my WZZ, and here I am drawing the curve which is area under this. So what the area will look like? It actually is going to go up to this angle, and then it is still going to increase, but at a lower rate. This is my okay. The wind healing moment is something like this. Now area under that curve. Initially the area under that curve, see, if you take any piece, it is much higher than that. 0, of course, it is much higher than that. Okay, so it can actually become much higher. At some point it can cross.
Yes.
But if it did cross here, then we are talking of a situation like this. But supposing it was much larger, it can never cross. So if it so in this particular case, it never crosses. If it never crosses, obviously the vessel cannot come back, because what also it means is that up to this I don't have enough area here to counter this area. Had it been smaller, so this was when I have changed the healing moment. See, on the other case, let me think that this was my original case. I have got enough area, but for some reason I have reduced my G. So now my this has become like that, and then I won't have any enough area. So therefore, what is necessary is that for a given wind healing moment, you must have enough area of the GZ curve, or for a GZ for a given GZ curve, it can only withstand certain amount of wind healing moment. Obviously, no ship can be designed to withstand all environment. Any building you design, it will be for certain wind. You cannot say there is 1,000 knot wind and it will survive. Okay, so that of course is a design condition. We will catch up on that in the next lecture. Okay, now this one will end here.